Recording is on.
Okay, hi everybody. This is another session on the trees. Let's do a really quick recap. Here is what we did so far. We completed array, strings, linked list, trees, and around 10 to 11 problems, 10 problems on each, and now graphs, and not graphs, sorry, in the trees. So we started trees. We completed the in order, pre-order, post-order, and tree zigzag. This is where Karunya helped on that. So, and another way, like feel free if anybody want to share the problem, and I will become student, and you come and present. No problem at all. So I will also learn new things. So if anybody practiced anything, Mudit or Cecilia, even Karunya again. So if you want to present, please let me know so that I will post that message to everybody, and you can also present. Okay. So last week we discussed about three BFS. BFS has three kind of concepts. First one is breadth first traversal. What is it's kind of clear definition and how to traversal. Like we already discussed in the tree zigzag. That is also kind of BFS, because BFS always goes level by level, right? So one first level, and they traverse the second level, and then third level, and then fourth level. You traverse either way, any direction, either from this side or that side. It doesn't matter. Once you are covered one level, you go to the elements on the next level. Okay. And that's the BFS. And traversal is just traversing all the nodes, and searching is basically you're traversing until you find a desired node. Once you find the element, you stop searching or you stop traversing the tree. Okay. So these are all exact same concepts, but just traversal traverse the entire tree. You visited every node of the tree, which is order of n. And breadth first search, it means like you traverse or you travel until you find the node you want to search, or you complete the tree. Once you complete the tree, if you did not find the element, you simply say not found, element not found, right? And both have order of n, because in the worst case, even you have to search all the elements. If the element is like, let's say I'm asking you to find 10. In order to go to 10, you have to visit every node, 1 2 3 4 5 6, all the levels, and finally you're able to find 10. So the worst case is order of n, which is like all the elements you may need to traverse, um, you know for this. So order of n is the algorithm, like a complexity for BFS. And today we are going to discuss more deep into the DFS. What are the differences and how it is differ from BFS, and what is the advantages, why we doing it. It's kind of a little bit dive deep into DFS. So before I start, I want to see if anybody want to explain what DFS is. Depth first traversal, depth first search. So I just want to know how much you guys know about this, so that I will start from there. Anybody want to share how DFS works compared to BFS? Feel free, just talk. Just it's just normal collaboration. Can you guys hear me?
Yeah, yeah.
Yeah. So I just want to know how far you kind of just explored, how far you explored the concepts. So
So, so we will start from the root node, and then
mm-hmm,
like suppose we start from the one, and then we
mm-hmm.
go to deep in that like till that what will say
the
in direction in
depth.
that direction in depth. Yeah,
Yeah, and basically you pick one of the childs and go to the end of that chain,
yeah,
right?
yeah.
Okay.
Then we will go back to root, and then look for the
Mm-hmm.
like if we have searched left node, then we will go to look for the right node.
Mm-hmm.
and then we will repeat again, go to depth of that,
yes,
and
that's
then
good.
come
So
back. Yeah,
mhm,
yeah,
come back
that's
to
how.
3. Yeah, so that's exactly how DFS works, right? So basically depth first, you go, this is called depth, right? Like a depth of a tree, or not a tree, depth of the well or a hole. If you are digging on the thing in earth, so you will say this is the depth. So breadth means this is the breadth. So how much breadth of this whole site or land or a house. Breadth means like horizontal thing, and depth means you will go down and then you will see the depth of this particular thing. So right, so that's what it is. Basically depth first, you will go all the way and see how deep it is. Depth means like deep, how deep this particular child it is, right? So and here if you look at this tree, this is not a binary tree, right? You guys already know the difference, right? Binary tree basically, anyone can share the binary tree? What is binary tree, and is it binary tree or no?
Binary tree has at most two child nodes, right?
Yes, exactly. So at most two childs, but here it is not binary tree because
Like 3 has 3 childs,
exactly.
like
So
the
the
3
one
node.
has three childs, and even three. If you look at three also has three childs, right? So it's not a binary tree. And let's see, is it binary search tree? Did I have I explained binary search tree? I don't remember. So that's the next concept anyway. But anyway, we'll discuss later. So this is not a binary tree, we know, because this particular 1 and 3 more than two children. So but it is just a tree, just a normal tree, right? So this BFS and DFS works on any tree. So it could be on binary tree, it could be on normal tree as well. So but in order, pre-order, post-order, what we discussed before, I think that will work only on the binary trees, because that's a binary tree traversal. Because in order, pre-order clearly says here, right? Left, root, right, node, like a in node means root, n means root, basically left node right and node left right. So these are specifically binary tree traversal. But BFS and DFS are just general tree traversal. Basically these traversals, that is the difference between, because it's not, there is no left right in the normal tree. It's like what, 2 3 4, there are just three childrens of one. You cannot say this is 2 is left or 4 is right or something, because it could be three children, it could be 10, or it could be 1,000, we don't know. So one could have the node 1 has n number of children, right? So in this kind of tree you cannot traversal using the in order, pre-order, or post order, because there is no left or right. So these are the two basic traversals for normal trees. Either BFS, which is go breadth, cover each breadth of the tree, each level, or you can go by basically depth of the tree. Okay, is that someone joined? Hey Shivank, welcome.
Yeah, hi, sir.
Hey man, how are you doing?
I'm doing good, sir.
Great, awesome. So, if I remember, 2 weeks back we discussed on BFS.
Yeah,
Have you joined? Have you joined 2 weeks back? 2 weeks ago.
I have joined, sir.
Awesome. So we covered the breadth first search, right? Last
Yeah,
week, last time. So
yeah,
now we are covering a depth first search, going depth of the particular node. Okay.
yeah,
So the main difference here, as I'm just explaining the differences, the main difference between the depth first search and breadth first search is the way you traverse the nodes of the tree, right? So do you have idea on the in order, pre-order, post-order, Shivank?
yeah. I know what is in order, pre-order, and post-order.
Yeah, basically these applies to binary tree, right? Only the
How you
tree which
traverse
has
the?
only two nodes, right?
Yeah,
So The if any node has two nodes, maximum two nodes, that's the main difference between the binary tree and the normal tree, right?
Yeah.
So do you know, is this a normal tree or binary tree? The tree which I am showing here, is it a normal tree or binary tree?
It's a
Shivang.
normal tree, sir. Normal.
Normal tree, yeah, because 1 and 3 has 3 nodes, right? Not just 2. The 1 and 3 are violating the rule of binary tree, right?
Yeah.
So in this case, as I said before, like in this case, the we cannot apply in order, pre-order, post-order. Those traversals may not work because we have, it could be 3 nodes or it could be 1,000 nodes. We don't know how many nodes one has, and of course we are seeing now. But if you are putting this in memory, you can add n number of nodes, right? So one could you can store under one, you can store 1,000 nodes or million nodes. There is no limit. So in this situation, how can we traversal? So breadth first search is one technique where you cover each breadth of the each level, right? And the depth first search is basically depth. You go to the depth of the particular node, and then come back and visit the another node. Okay. So now we started at 1. So there is no specific rule. You need to pick 2 or 3 or 4. You can pick any of those. There is no rule. It's not like in order, pre-order, they take left or then root and right or anything. So it's just you have a freedom. When traversing, you have full freedom. You can pick any of the nodes. So let's say you picked 4, right? So you start from 1, and let's say, let me change the color here. Okay, let me take blue. So you start with 1, you go to 4, and then you don't see the other nodes. The 2 and 3 are other children, but you don't care. First you see how depth is this, how depth is the tree by traversing from 4 to the next node, 9. So you go all the way to the down until you end up visiting a node which doesn't have any children. So 9 doesn't have any children, right? So you will see the depth of the particular leaf or particular branch. You can say anything. So now once you're done, you go back a little bit and see, do we have any nodes for any children for 4? Oh, 9 is the only children, right? So done, we are done processing the 9, and we are done processing 4 because there is no children for 4. Now you go back and see, do we have any children for 1? Other children, yes, we have. 3 is another children, and 2 is also another children, right? Now we explore one of those. You can explore either 2 or you can explore 3. Let's say you explored 3. Okay. Now you visit the 3, and then after 3 has 3 children again, right? 3 has 3 children. Again, the same rule applies. You can pick any of the children. Let's say you follow the same pattern, you pick the 8. So once 8 is completed, right, you will go to the 10. And once 10 completed, there is no children here. Now you go back to the 8 and query what are the other childrens of 8, because 8 is the processing of 8 doesn't complete unless you traversal all the childrens of 8, right? So you completed 10, but there is one more children of 8, which is like 11, right? So you complete 11. So now you completed depth of both the sides. You completed the depth of left, like not left. The Of course we have only 2 nodes here, left of 8 and right of left of 8 and right of 8. You completed full depth of node 8. So now you go back to the 3 and query the next node, which is 7, and then you go back again, and 6, and then 12, and then all the way go back to the 1 and see what are the other children's, 2 and 5. So that's how it is it clear, or any confusions here?
Yeah, it's clear.
Yeah,
Awesome.
it's clear.
Yeah. So basically, I would say, like, it will go and dive deep, right? So and then it come back. So now let's see how to do this. So I explained the full algorithm, how it works. Now think about how to write the code for this. Don't look at any online sources. It just if you look at, you can find the algorithm anyway. But I'm just asking, like, just think about it. um, what data structures will help to achieve this traversal? So last time BFS we used, what data structures we used? Can anyone tell?
Q.
Exactly. So
Q.
the queue, we used a queue. That's a very good data structure for, the BFS, the breadth first search. And so can anyone tell which data structure helped to do the DFS? Do we think the queue will work with DFS as well, or any other data structure? What are the other data structures we have? Like we have stacks, we have arrays, we have hash tables, we have, what else we have? We have maps, and yeah, or linker list. We have another great data structure, basic data structure, which is a linker list. So any which one will be helpful here to, um, you know um, will be useful to traversal the depth first search? Any idea? Anyone want to say anything, or just you want me to just go ahead and explain?
So like we can use like maybe stack.
Yeah, maybe stack. Let's see, why maybe stack, why not queue? So that's a good
So
answer. The stack is actually answer. Stack will be helpful, but why stack? Why can't we do with queue? Shall we try with queue before going with stack?
yeah.
Okay, just let's try, let's see why it is not working. So as I said, we want to visit one, so let's put one, as discussed last time. We will put everything in that data structure and process from the data structure. That's the easiest way. So we'll put everything, not everything means one each node. So we'll put one there, and then process one, we printed one. So stack always, like queue always works in with two things, right? Entering from one side and exiting from other side. So one entered from here and exited. Now M1 is not there here. So now you printed one, and you are going to add the children of one, right? You're going to add 2, 3, 4. They will enter from this entrance of the queue. So now, as I said, let's say, no, maybe you added this way. As I said, we want you added 4 and 3 and 2, because we want to visit the 4 after 1. We want to visit 4, right? So now you added this way. Okay, which is good. So now you printed 1. Now you take the 4 and you printed 4, which is good. So we are doing good so far. Now after printing 4, we need to push the elements of the 4, or the children of 4, into the data structure, right? So 4 children is 9. So you have to push the 9 to the queue. Where do you want to push? Like when you push, is always entering here, right? The element enters from the rear. So a 9 enters from here, and 9 will be, entered after 2. After 2. So 9 is here, right? So now you're done with 4. Now you want to take the next element and print it. So now 1, 4, 3. So which is not the right output, right? Let's write the output of the DFS, which we traversed before. What is the output? The one we traversed before? 1, 4, 9. Can anyone help me to complete the DFS? The output of DFS? 1, 4, 9. What is the next one we need to print?
3, 8, 10, 11,
3, 8, 3, 8, 10, 11. Very good. And
7,
then
6, 12,
7, 7, 6, and then
12,
12.
12, and then,
5,
are you sure? Is it 5?
2, 5.
Exactly, 2, 5. Sorry, yeah. So that's good. So this is what we want. We want, this kind of output. This is one of the DFS, by the way. There could be another, like 1, 2. You can also do, as I said before, if you pick, instead of 4, if you pick 2, the output could be different. 1, 2, 5, 3, something like that, right? So These are the different like valid DFS outputs. But what are we getting here? We are getting 143, and then if you take 2, we have 1 4, like this, 1 4 3 and 2. You are just getting a BFS. So because the way the queue works is basically it will give you, you know, elements which you just inserted, right, in the same order. So that's the thing. You inserted 432 and you will get the same thing, 432. So that's why BFS, the breadth first search queue, is the best data structure for breadth first search. So why stack works? Let's look at the other side of it. So now we don't want to use queue. You understand why queue doesn't work, right, for DFS, right? So
Yes.
let's see now why stack works perfectly. So now we will put one, like as I said, we just put everything into the data structure before processing. We did not process anything. We got the one and put one here, and there is no other input at the beginning of the algorithm. Okay, now let's process the element. Let's take the one from the stack and print it. We printed one, and there is no element in the stack. Now after printing the one, we need to look at what are the childrens of the one. What are the childrens? 2 3 4. Let's say if you are asking children 4 3 2 also, you can, as I said, the order doesn't matter. So let's say if you are asking for children, we got the output like this, 4 3 2. So we will put those elements into the stack. So let's say we got the similar output. Let's say we got 2 3 1. The order doesn't matter. Let's say give me the children of 1, and then we got the output saying 2 3 4 are children of 1. So let's take 2, as it's kind of iteration, right? So you will iterate through the children and put it in the stack. So output says 2 is one children, let's put it there. 3 is another children, let's put it there. And 4 another children, let's put it there. Okay, do we have any more children? Here I keep on asking. It's kind of for loop or loop iterator, whatever in Java, right? So you simply iterate through the list of children, and you keep putting those children into the stack, and then we are done. So once there are no more children, we are done for that particular processing of the one. So one completely processed. Now now look at the stack. Do we have any elements in the stack? You have to do this process until the stack becomes empty. That is the rule. So we did the same thing for queue, right? We are keep processing the queue until queue becomes empty. That is the rule here. So queue becomes empty means there is no more nodes to process. You are completely traversed the tree.
Sorry to disturb. Can you explain this again?
Sure,
This
sure, sure. Is that
part.
is that stack completely coming showing here, or maybe is it cutting? You
No,
can see
it's
my
not.
entire screen, right?
I'm not able to see your cursor only.
You can see the my full tree and also the stack on the right side, correct?
Yeah, yeah. 432,
Yeah.
right?
Okay. Yeah, 2 3 4 on the right side of the stack here.
Yeah, I can see.
Okay. So basically what I'm saying is, um, so we need to print the elements like this, 1493, right. So before printing anything, what we are doing is we are starting from the root and taking the node, and we are putting in the data structure. So we already placed one, and then we processed one and printed one here, right? So after printing one, what we need to do is we need to query the children of one. Who are the children of one? What are the child nodes of one, two, three, four? Correct? Is it right?
Yeah.
Following, right? Shavank. So
Yes.
all those three
Yes.
nodes, yeah. Once you iterate, once you are querying, once you are asking, once you ask the children, you will get the children. So you don't print the children. We don't want to print the children as it is. We follow the same rule. We simply put them into the data structure, whatever the data structure you are using. So in the BFS we use it queue. In the DFS we use it stack. So we will put the elements in the same order as you get. I got 2, 3, 4, and I put it in the stack. The stack works this way, right? You put the elements on top of each other, right? Stack of plates, stack of books. You know the examples of stack, right? So
Yeah.
you placed all the elements of the stack. Now you say that you completed processing of one because you printed one and you placed all the elements of the one into the stack. Now what we need to do is we need to do the same procedure until the stack is empty. That means we need to do the same procedure. Means first step is remove the element from the stack, and that is first step. Second step is print the element, and third step is query the children of that element and put it in the stack. Just three steps. First one is, of course we have one more step here. First one is put the element in the stack, or then if the stack is not empty, remove the element from the stack, print it. Second step is printing, and basically first step is removing the element from the stack. Second step is print the element from the stack, and third step is query the children of that element and put it in the stack. These are the just three steps we need to follow. So now first step, remove the element from the stack. Which one? If you want to say remove, what is called remove operation in the stack? What is the popular name for removal of the element from the stack? Can anyone
Pop.
tell?
Pop.
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 So you can see here, right? Pop is the operation. Once you say pop, it will give you the top element of the stack. Correct? So we will get it. What is the second step? Print. First one is remove. Second step is print. So we printed 4. Now what is the third step? Childs, add childs, basically AC. Add childs. Basically, query the childs of this node you just printed. I printed 4. We need to ask for the children of 4. Who are the children of the 4? What are the
Like
child nodes of the 4?
9.
9.
9, right? You removed 4. Now the stack is only 2 and 3. And we got one more child called 9. We will put the child on top of the stack. We'll put the child here. That's what the third step says, right? Third step is add the childs into the stack. So we got only one. 4 has only one child, and we put that on top of the stack. Now we're done with 4. Now repeat the same step for next element. Pop it. You need to pop. If you pop, what is the element we will get? Which element you get it if you pop the stack?
9.
9.
9, right? So 9, print 9. So I just popped 9. I printed 9. And then second step is printing. Just printed. Third step is same thing. Query the elements of the stack. Children of the 9. Query the children of the 9 and put it on the stack. But if you ask for children of 9, what you get? You get nothing, right? 0. There is no children of 9. Now what you need to do? Simply nothing. You don't need to add anything. Go back here again. Go back here and check, do we have any elements in the stack? Because that is the main thing, right? These three statements which I mentioned here, let me highlight this. These three statements here we have to repeat until until the stack is empty. Okay, are you guys following so far?
Yes.
Let me know if any.
Make-
So now the stack has two elements, right? 2 and 3. We will follow the same step. Remove or pop the element from the stack, which is like this. Remove 3 and print the element. I printed 3, right? And what are the children of the 3? And put it in the stack. So what are the children of 3? Can someone tell me?
6, 7, 8.
Exactly. See, we got 6, 7, 8. And what is the step here? We added, we popped 3, we printed 3, and we added the children into the stack. We are done with 3. Now go back here, and next the same step, remove the element from the stack. Now what element we get?
8.
8. And we printed 8. And what are the children of 8?
11, 10.
You guys following so far? See the 2 there. See the 2 is still hiding at the end of the stack. It's kind of lower. It's a very, very low, and the first element we inserted, because we need to process this whole depth of 4 and the whole depth of 3, and then only you come to 2. That's why 2 did not get a chance to print yet. Are you guys following how it works, or is it now what we did? So we printed the children of 8. We completed 8, and then we print 10, and then we will pop 10. We'll pop 11, and we printed 11 here, and then we popped a 7. We printed 7 here, and then we popped. There is no children for 7. We popped 6. We printed 6. Now, after printing 6, what will happen? What
Like we
is
will
going to be inserted into
like 12.
12, right? 2 is, so before even 2, it comes 12, because that's how it is, right? After processing 7, after processing 6, so 6 completed, and then 12. So we need to process 12 before 2. That's why the 12 goes to on top of 2 here, and then 12 will be processed, and there is no children for 12. And then finally we will get the chance to print 2, but we don't stop there. Stack is empty, but by the time empty, but there is one more children for 5. For one more children for 2, we will put 5 there, which is like 5 there, and then we completed 2 as well. We completed everything. All the nodes are completed processing. Even 2 also completed, but after finishing 2, you added one more last element 5. You did the same thing. You processed the same thing. Pop the element 5 and print it. Pop the element 5 and print it, and then see if we have any children for 5. There is no children for 5, and then you complete it. Now you come back here and check, hey, do we have any elements in the stack? Do we have any elements? No, right?
No.
That's the end of the algorithm. Finally, stack is empty. You guys followed so far? Any questions, or is it easy or difficult?
Understood, sir.
Okay, got it. Awesome. You can just simply call me Suresh rather than saying Sir or anything. Just, of course, I am age-wise, I'm, I'm elder than you, but just call me Suresh. So it will be easy. Okay.
Yeah.
So, okay. Any questions? So, this will work for any kind of any depth of tree, right? It could be 10 elements or 20 elements or even million elements. You can just process the same process. Of course, the problem is if you have million elements or like kind of that kind of huge elements in your memory, you also need very big stack, right? You're adding all those elements into the stack. Is it someone joined, or is someone dropped and joined again? Okay, anyway, so
Like one question, Suresh.
yeah.
Like when we print one element and then push its children in the stack, so like we have to push from left to right, right? Like
Stack doesn't have any left or right? Stack has only top.
yeah,
Oh, you
like
mean you mean you
suppose
mean you mean like you mean like you mean like taking the elements? You mean taking the elements from the tree?
yeah, Like suppose we print 8. So like when we push 11 and 10
Uh-huh.
in the stack, so we have to push first 11, then 10.
It doesn't be like that. As I said before, the it could be like 8, 11, 10. That is also DFS, right? So there is no rule that you need to go 8, 10 after 8. There is no rule. You can. So that's what I'm saying. Let me put another DFS. So this is also DFS, like one,
Okay, okay.
1, 2, 5. So you can go to, you can navigate any children. There is no rule that you need to process 10 and then 11 or 11 and 10.
Okay, okay. Got it.
So this is also one example of the DFS. So 1, 2, 5 and then 3. So I'm putting one more DFS, one more DFS output here. So you processed one here, 1, 2, and then 5, and then 3, 7, 6, 8. This is also DFS. Like you processed. Oh my God, this is like so crazy. Here, let me remove these arrows. So we have 7 here, right? So 3, 7, 6. After 3, you processed 7, and then you completed 7. You processed 6. After 6, you processed 8. There is no rule, right? So, and after 8, you can process, 10 or 11. Let's say you process 11 and then 10. Got it? So it
Yeah,
could be
yeah.
in any direction. Yeah, there is no left or right. As I said before, this is not a binary tree. So it's kind of, every node can have n number of children. So so basically you will query in a for loop whatever the language that will give you the list of nodes, right? So it could give in a order way, or it may not be in order, but you just process as you're getting from the system. You just say, hey, give me children of 8. You will get the bunch of children and you put them into the stack, and any order is fine, right? So cool. Let's jump into this is a DFT, I would say, traversal, right? It's not a searching. We haven't done any searching. DFT. So depth first traversal. You traversed all the elements of the tree, right? So depth first search is exactly the same thing, but you will stop until you find the element. Let's say I will ask you to find 8, right? So let me remove this. It's so clumsy here. So if I say find 8, what you do basically? So you start with the same process, right? You start with the same depth first search process. Okay. So you process the same thing. You start with root 1. You don't know whether 1 is whether we have 8 here or not. You will compare with 8. You want to find number 8. So we'll take the root and compare. Is it 8? No, it's not 8. And then you simply follow the same process. Before processing, of course, we'll put 1 in the stack, and then we'll process whether we remove the element from the stack and compare. That's the process. You always put the elements in the data structure, and then remove the element from the data structure and then compare. So if I say the steps, I can outline the steps again. So first one is, pop pop the element, and then compare, and then add children. AC, add children. So you're popping the element. Basically you compare, you one here, you popped 1 and you compared with 8. No, 1 is not equal to 8. And then add children. Third step is add all the children. You put all the children, like 4, 3, 2, right? So now you do the same thing. Pop the element 2. You pop the 2 and then compare with 8. Is 2 equal to 8? No. Add the children. So 5 will be added here. Now pop and compare. So 5 is not equal to 8, and then you pop one more time, which is 3. 3 not equal to 8, and then add the children of 3. So 4 is here. Add the children of the 3. 6, 7, 8, and then do the same thing. Pop and compare with 8. Yes, we found 8. 8 equal to 8, and then stop there. You found the element, success, and here you go. So you can simply ignore stack, or you can, of course, stack still has some elements, 7, 8, 9 is there, but you no need to process. You found what you want, right? So you return the algorithm there and say element found. So let's assume that this is a tree of employees. This is the tree of employees, and simply say, hey, find Shivank. Shivank is somewhere here. Okay, Shivank, in the data structure, here is the place where the employee Shivank, data stored here. All his name, his address, his phone number, his salary, everything in the database. So you will go in this depth first see until you find that this is 8 is the Shivank's, the employee number. Just assume that. So you compare each employee number with this object and see whether that employee number equal to this employee number. Nope. And there are 3 more children. Let's say this is CEO, and these are the managers, and the top level managers, and then you compare, each of these. Is this the employee number is equal to employee number of this object, this object, this object? No. Let's go to the next one. The same way, basically, breadth first search or depth first search, you just traverse the nodes and compare with whatever the key you're looking until you find the element. Okay, like if I say, okay, find element 55, what will happen? You process the entire tree in the depth first search way. You process all the nodes of one branch and all the nodes of other branch, and then you will go all the way. Finally you say, nope, the employee with ID 55 did not find. Maybe he resigned, maybe he never joined. So the input is wrong. Basically you're asking me to find something which never exists in our current database. Okay, so is it clear, or any questions on the depth first search? Shivank, is it clear? Karanya, I just want to hear, like, any questions, or is it clear before going to the next concept? Or I can show the code actually. If everybody clear, I can show the actual algorithm, how to write it, and all those things. Shivank, are you following there?
Yes, sir. Yes, Suresh.
Yeah. Yeah. Thank you. So yeah, that's how it is. Basically it just finding an object in a different way. Either it could be in a breadth first or depth first. So let's talk about the complexity. Can anyone tell the complexity of BFS? How complex it is, and what is the worst case?
It will be O of n for space complexity, and O of n for
Most complex.
traversing the tree.
Very good, very good. So O of n for space and O of n for time. For time, definitely O of n, because time complexity means like whether you need to traverse all the nodes in the worst case. Yes, in the worst case, let's say if you want me to find 55, there is no 55 here. But how do you know? Unless you traverse all the nodes, all n nodes, you don't know whether 55 is there or not. So in the worst case, you will traverse all the nodes. So the time complexity is order of n. But let's look at the space complexity. I don't think it is order of n. It could be order of n. Sorry, yeah, there is a worst case where you need to know, we need to store all the elements of a tree. Yeah, that's good actually. So sometimes, I can give an example where, like, if you look at here, we are not storing all the elements at the same time, right? If you look at here, so 764 is here, four, like 764 in the stack, but at this time we already processed some of the elements. We already popped some of the elements, right? We don't in this particular tree, we you don't put all the elements of the tree into the stack at any moment of time. At any moment of time, it is less than an elements on the stack. Do you guys agree? Because you keep popping and then
Yeah.
popping and then adding, right? So in this particular tree, the space complexity is not order of n, but there could be an example. Let's say this is a very, very big tree, very big tree with a node called A. This is a very big tree with how many nodes? Just one node. This is also a tree. Why not? Right? This is also a tree.
Yeah.
Do you guys agree? This is a tree. This is also a tree. This is just one node. That's it. So this tree size of order of n is basically n equal to 1 here, right? N equal to 1. How many elements in this tree? Only one. And in order to process this tree, BFS or DFS, we need that stack, and you need to put that element here, A, and then you need to remove the element here, print it. So now the space, how much space we need? Order of 1, which is order of n. So this is it's kind of worst case. You can think of that way. It's kind of you need you need number of elements in the tree equal to number of spaces you need on the stack. This is the case. Or I can also give another funny example. Maybe a tree like this. Just assuming. No. Tree is something like this. In a funny example where you can think of a tree like a very big tree, a really big tree like this. The parent node is like this, and you have children of all the nodes in the children. Let's say you have 1,000 children for this particular node, right? So you need to take a stack of 999. Do you agree? Or yeah, because let's say no, let's say this node has this A is the root, and you have 999 children. Just an example. Total 1,000 nodes in the tree. A is the root, and A has 999 children. So you need a stack of 999, correct? Because you process A, and then you need to put all the 999 nodes into the stack. Do you guys agree?
Yeah.
Because the second level, that's it. Let's say you don't have any children for these 999. There is all the 999 childrens are just leaf nodes of A. Now you need a stack size of 999, and the whole n equal to here n equal to 1,000, right? You have 1,000 nodes, and stack size equal to 999. So there is just a difference of 1, right? It's a constant number 1. So it is negligible. So you need space of n. So this is order of n. Space is also order of n, because you need exactly almost the same size of the number of elements of the tree. This is another example where the space complexity is also order of n, which is good. Which is good and which is not good as well, because just assume that if your database has an employees of million employees in a tree, and you employ objects, and you want to process using DFS or BFS, you need to take another stack of million size, because you need to take a really lot of memory in order to process it. You already have like, let's say this million is taking a, let's say 5 GB, or let's say assume 5 GB in your RAM, and you need to take another 5 GB to process this. Just assume that like 10 GB of memory you're consuming to process this tree, which is crazy, right? you need to have a really big server to process it. 10 GB of data in the particular algorithm. I don't think we can run in our laptops. You need to have a really big server to process that 5 GB of employee objects using the BFS or DFS. Got it? So that is the main drawbacks, I would say. This is the kind of, sorry, you're saying something? Somebody asked some question. Modit, are you, is it clear?
Yeah,
Yes,
like
it is.
Yeah.
I
So
was saying,
basically,
it is the
um,
worst case.
yeah, yeah, it's a worst case. Yeah, that's I totally agree. So let's assume the worst. We always need to consider the worst case, because if you are waiting for that last employee, if you want to print the employee address of that particular last element, what is the point? Like, you need to process all the elements, right? We don't know the, sometimes you ask, you want the address of the first employee or mid of the employee, and sometimes you want the address of the very leaf node or the employee object which is at the bottom of the depth or tree, right? So in the worst case, what happens is the whole memory, like 5 GB of objects in the tree and another 5 GB of the stack you need to maintain in the memory. So it's really, it's really big processing power required in order to process. So, but that's how it is. This traversal. This is how the depth first search and the depth first. So if you are looking for an employee who is at the maybe somewhere in the first half of the tree, right? Let's say the DFS is best algorithm. If you think that the object can be easily find if you go to in one of those branches. Okay, let's say I'm asking you to get the employee address of an employee who is at the last level, maybe just junior software engineer. I know Shashank, let's say, you can just give an example. Let's say Modit, you just joined the company, right? Let's say your company has 1,000 people, and I want the address of the Modit's object. I know, so this guy just joined, so he will always at the kind of root like leaf node, right? So you will not be at the CEO level. I know that you will not be at the board of directors level. I know that you just joined, so you will be at the one of the managers. You will have one of the managers, and you will be at the leaf node. At least not leaf node, maybe in the middle. I know that you will be somewhere here, at least on the bottom side of the tree, right? Then I no need to go for breadth first search, because there is no point of searching for each directors and then directors, the next level of people and next level of people. I can just go with one, and let's see the down. Do we have Modit here? And see one and see, do we have Modit here? So because the context, I know that you are a senior, you are the junior, like not junior, kind of a new employee joined at this kind of position. If I know that context, then I can see which algorithm best looks best algorithm. What is the best algorithm works for me, right? So I know you just joined as a software engineer under a manager. I can ask, I can start from CEO, and then I will say, hey, what are your one of the, give me one of the managers, and then I will go down and see, do we have Modit in that direction or not. I no need to, I no need to go for breadth first search, right? That's a bad idea. Like searching for in each level. You guys, you guys getting what I'm saying, or any confusions here?
Yeah, yeah, it's
So
clear.
yeah, context will help. That's what I'm trying to say. The context. Let's say another example. Let's say, hey, there is a high level board member called some Mark. There is a person called Mark, and he's I know somewhere he's a board member or maybe director. Then what do? You don't go the depth first search. There is no value of doing it, because if you go depth first search, you will go all the way to the Modit, and then go back here all the way to the Shashank, and then go back. What is the point? You know that context. He's a senior director. He could be director level or board of directors level or directors or senior manager. Then what do you do? Go for path first search, level by level. Let's see if that particular manager mark is in this level, or in this level, or in this level. You don't need to go down. Even if you have million nodes under these managers, you don't need to traverse, you don't need to check those people, because you know this guy is somewhere on the top. You got it? So that context will give you which algorithm works for you, or which algorithm is best to choose. So in this example, we don't have any context. I am just saying find 8. We don't know whether 8 is an employee or a manager or a board of director or something. If you don't have any context, there is no choice. You just choose either DFS or BFS, and then traverse all the nodes. Okay, I think I'm explaining too much. I don't know whether I'm confusing you guys, but I can show the algorithm if you guys don't have any other questions.
Yeah, it's clear.
Yeah, I'm just trying to give more realistic examples, like where this works, and what is the main point of that. That's where I really explore, like when I started these algorithms, why are we doing all these things, what is this traversal, where really applicable, why we need to do this. So in real time examples, these are the different processing operations, like kind of ways of processing the data, right? So anyway, so you guys looking at my the here, can you guys look at the code,
Yes.
right? So here is just a node class, here is the data, and as I said before, there is no left or right, it's just a list of nodes. This node details, basically list of, this is C sharp, by the way. I am C sharp guy, and it's almost like Java. So so we have a node list here, children, and here is the constructor. And if I say get children, as I said, I'm asking this particular object saying, hey, give me children. So it simply returns all the children at one time. Just hey, this is the children, take it. So it's a public method. So I created these nodes exactly the way I represented, 1, 2, 3, same thing. I just added all the nodes here, 2, 3, 4, and everything, and then I added the children here. This is a setup. All the setup is completed here, and here is say, hey, depth first traversal of n1. Here is the n1. N1 is the node 1, which is n1 has where is n1? N1 is the node n1, node 1. So I'm asking, hey, start from the root and complete the depth first traversal, and then run DFS. Run the DFS algorithm. Start from root n1, find 8, and find 15. As you said, there is no 15. As you see here, there is no 15 here. We are expecting false. And if you say find 8, there is 8 here. So we are expecting true. So these are the methods I created. So here is the depth first traversal. So if I need to increase, I keep on forgetting. Oh, zoom in. Okay, this is zoom in. Okay, can you guys see now? Let me know if I need to increase the font again. Is it okay? Okay.
Yeah.
So is it good? So now here is the same thing. As I said, the same steps which I explained. First, this is the base condition. If the root is null, there is no point of doing anything. Just return. This is very important in interviews. So these base conditions, or the null check conditions, are very important. Somehow somebody called this method with a null object. So we should not crash the application. So we should not crash. Algorithm should not crash. So should not fail, basically. So we'll say if it is null, return, no need to do anything. This is a traversal. So what we do, as I said before, we create a stack and we push the root. Initially we need to push something into the stack, and then we are taking a just variable called node. And as I said, we need to process the steps until you complete the stack. So until there is no more elements on the stack. So as I said, step 1, pop the element, and we pop the element. And step 2, what is this? I don't know why it is. Oh, wait, I did a mistake here. Or maybe equal to. Oh, I removed something. Okay, I removed something here. Okay, now this is step 1, right? Pop element, pop the element, and the step 2 is basically print the element, and step 3 is add the
Children to the
yes
stack.
children to the stack. That's a step 3. Only 3 steps. So first we popped the element, and we got the element here, and we printed the element here, node.data, which will print it. And then for each node.childs, or actually I should call get childs. Why it is not coming? There is a method I created, right? Here is a method I created, get child nodes. No, let me see why it's not showing. I can call that method as well. So either I can say childs, which is public, or I can say, hey, get child nodes. So this will give you all the childs, and I'm iterating for each. I hope you guys know about this for each. This we have in almost all languages, we have for each. And for each child, we are pushing into the stack. Right? Add children, that's what the number 3. So again, it will go back here, and then it will process the next element from the stack. So very simple, just 3 steps. But just to get the concept of these 3 steps, we spend more than half an hour, right? Around 40 minutes. So this is the complexity of the algorithms. The actual algorithms are very less number of lines, but in order to get the full understanding, we need to spend that much time to understand how it works. Okay, so next one, as I said, depth first search method is here, and run depth first search is here. Run means basically this will run this algorithm, and here is the depth first search. And if the value found, it will say, hey, value found in the given tree, and if otherwise value does not exist in the given tree, it will print it. So this particular algorithm, this particular run DFS will run this depth first search algorithm. So this depth first search algorithm returns bool value if based on the result, whether you found the element or not. So here is the value to find, and if the root is null, you simply say there is no value. Otherwise, you will do the same steps, push the element of root into this pop, and it's exactly the same steps as I said. First one is pop the element, and the second step is compare the value. Third step is add children to the stack. So here is the thing. So you pop the node here, and you add the data of the node with the value to find. And if the value matches, you simply say, hey, return true. And if not, what you need to do, you need to add all the children into the stack. Is it clear, anybody? Or no one is asking any question, or I don't know whether you guys
It's
are
clear. The steps are so clear, Suresh. So it is easy to
awesome.
understand. Yeah.
It's very easy to understand. I'm just putting some comments to make it clear. So basically, you guys can ask, hey, if I'm asking you to find an employee object of Modit, just returning true is not enough, right? I'm not asking like, hey, is Modit in the tree or not? That is one algorithm. Let's say, hey, if the Modit is there in this employee tree, give me his object. Then you simply change, instead of bool, what you do? You simply change to node, right? you return that whole object. You don't return just true or false. If you want to return the whole data, whole node object, you can simply change the return type of that. And you can simply say, hey, here is the Modi object of employee called Modit. Do whatever you want. You want to increase, you want to hike, you want to give a bonus to this guy, give it, right? So that's how it
Yeah,
is
that's
before
great.
processing. Like, yeah. Joining bonus, you join the company, right? You're entering into the new project, so we are giving a bonus. So something like that. So if you want to process anything on a particular object, you need to extract that object from the memory. So that's how it is. um, Otherwise, here is another condition here we forgot to say. Like, if we complete the entire thing, you completed all the elements, and finally you end up saying there is no value. There is no the value value to find is not in the tree. You simply say false. So we traverse the entire tree, but we did not find the value to find. So we simply return false. So simply let me run this code quickly, and then we are done. Actually, it's exactly at the time. It's already 10:30. Sorry guys, it's maybe very late for you guys, right? For me it is 9 p.m, 9 a.m, and it's 10:30 for you, right?
No problem,
Okay,
Suresh.
where is the output? Great. uh why where is output here? Show output here. Yes, terminal. Is it terminal? Is it still running? I don't know what's happening here. Yep, it's still running. So we got the output here. See, depth first search. This is exactly the what we are expecting on this tree, right? So 1, 4, 9, 8, 10, 11, 7, 6, 12 to 5, right? And then if I say 8, found in the tree. If I say 15, does not exist in the given tree. So it's the same outputs what we are expecting, and that's it. Any questions? So if there are no questions, I can give you the inputs what I'm going to cover the next sessions. The next sessions is tree binary tree. Sorry, it's a binary tree level wise processing. One of the sessions, if I remember correctly, Karnya, you covered this, right? Maybe we can, if anybody missed, we can cover
Yeah.
again. I can show this again. Basically, given a binary tree, create linked list of the nodes at each level. The binary tree depth is D will get D linked list. This is also a popular question in the past, so I will cover one more time. And the next concept is very important, very complex: binary search trees. These are really like, I would say, comparatively complex than normal trees. Binary search tree, and finding an element in binary search tree, inserting new elements. So if you look at the, as we discussed in the just now, it's very tough to find elements, right? You don't know unless you know the context, unless you know whether this particular guy is a leaf node, a kind of a new employee or board of directors. If you don't know the context, you cannot you cannot easily identify. You need to traverse all the elements, and you are wasting a lot of processing time and power and a lot of memory. That's the main drawback of these algorithms, DFS and BFS. So, and also the tree is not in a particular order. You can have n number of children. There is no restrictions on this tree, right? Um, there is no left node, right node comparisons. Or if you look at binary search tree, we discussed in the beginning, there is a rule, right? Even a heap, the heap also, there is a it process in a, the heap data structure or the tree created with certain rules. So even binary search tree has certain rules when you are constructing the tree. So those rules will help you to find the elements easily, and also insert the elements in a proper way, and deleting the element. So we can we so and also the finding in order successor, which is very important question in the interviews. So these are the very, very important concepts. So we can discuss those in the coming weeks. um, yeah, and these are the questions. Yeah. Okay, any questions? Anybody want to say anything or any questions?
No, Suresh.
Cool. Is this time is okay for you guys? Is it manageable to continue this time?
Yeah.
Yeah, it's fine.
Awesome.
Yeah.
Is it fine for you, Shishwank and Modit?
Yeah, it's fine.
Yeah. Yeah. Yes, Suresh.
Awesome. Thank you, guys. I think, yeah, we are done for today,
Share the
and
code.
continue the next.
Hello.
Okay, awesome. What you say something, Shivang? You saying
I
something?
said you can share the code of BFS.
Yeah, yeah. Oh, code.
Okay.
Yeah, sure. I will share the code immediately. So I can, let me show you. This is the. Do you guys know about this one? The online GDB. You might already know about this. So all the code I'm putting in this online GDB compiler. So I will post here. I have all the algorithms of trees and also other things here. So it's becoming slow here. Just a minute. So 1 hour 33. Let me stop recording, or yeah.